Hi, in this video, we're going to take a look at regression analysis. So this is going to be a review. I'm going to be covering a lot of regression very quickly, very briefly, in a very shallow manner, because the goal of this video is to help prepare us for logistic regression. All right, so the theory of regression has been built up by far the most for linear regression, where we have a continuous target variable. Now, in logistic regression, we're going to have two possible levels, like success, failure, pass, fail, broken, not broken, true, false, sick, not sick, something like that. Two different levels. And in logistic regression, the math is a little bit more complicated than, just the nature of building it up. And what we're going to do is we're going to first take a look at regular old regression analysis to help get us familiar with the concepts that are important in logistic regression. All right, so let's get into it. All right, so for regression analysis, our equation is going to be a linear regression model of this form. All right, so something to take a look at is that I have predictor variables, which are our independent variables. Here I've got P of them. P could be 1, 2, 3, 4, 5, any positive integer value. And then I have coefficients multiplied by our predictor variables. Now, something that's important to realize is that all of these predictor variables have to be numeric. If I have categorical data, what I'm going to end up doing is converting to zeros and ones with dummy variables. And then we're going to have an intercept term, so y-intercept, and then we're going to have this little error term over here. So y is the dependent variable. It's continuous when we're doing logistic regression. Beta 0 is the intercept. So if I plug in 0 in for all my predictor variables, I'm going to get beta 0 plus the error term. Then all of the betas are the coefficients of my predictor variables, which are the x's. And then epsilon is the error term. So all other aspects of the situation, all other aspects of the data that's not accounted for with my model is actually housed inside that single epsilon there. Okay, so let's go ahead and let's build a simple linear regression model just to start out. So I'm going to use the MT-CARS data set. And we're going to say, hey, I want to know the relationship between miles per gallon and the weight of a vehicle. And we're only going to consider weight, and we're not going to consider all the other features of a car, such as cylinders and displacement. So what we're trying to do, we're trying to say, on average, overall, what is the relationship between miles per gallon and weight, regardless of what the other features of the car is. Okay. And so I fit a linear regression model. And so what I see is a negative 5.3 for the coefficient of weight. And then I see the intercept of 37.3. All right, so what this tells me is that if I had a car of zero weight, I would expect to be getting 37.3 miles per gallon. All right, that's kind of a weird thing to have happen. So here we can see that the intercept interpretation doesn't make sense on this particular model because zero weight doesn't make sense. Now, what's more important to us, what we want to focus in on more, is this negative 5.3. What this is saying is that if I increase the weight of the car, now I didn't take a look to see what the units of measurement are for weight. Shame on me, but I'm filming and I'm going to keep rolling. If I increase the weight of the car by 1 unit, I would expect on average for the miles per gallon to decrease by 5.3. Okay. And so we could use this to kind of get an idea of if I see a car, I have its weight, I have its miles per gallon, I can say, hey, is it overall fuel efficient for its weight compared to other comparable cars, right? Also, this can tell me if I'm developing a car, and maybe I'm designing one, I can check and see, well, if I increase, the weight to have, like maybe an extra spare tire or maybe an extra seat, we increase the weight to add a feature. Well, what will that do to miles per gallon? Definitely an important question during the fuel crisis. All right, and so we also have some hypothesis testing going on. using the t-distribution. Here's our t-statistics. And here we see we have very small p-values. So we reject the null hypothesis that the coefficient is equal to 0. Now, here we get an R squared estimate. And we also have an F statistic, an F hypothesis test coming off of this, which, if you're familiar with that, you can use that pretty nicely. All right, so now let's take a look at the plot that we get when we do this. All right, so there's a bunch of default plots that R gives us. So there are 4 default plots. If I want to see particular ones, I enter a vector of what I want. There are 6 of them, 6 possible. The default is a selected 4 of them. I take my linear model, put it into the plot function, and if I leave this alone, if I don't have the which parameter filled out, I'll get the default 4. If I want some more in there, I can just control it, and I can pick and choose. So the first one is the fitted values on the horizontal axis with the residuals on the vertical axis. Now, when I look at these plots, I want to not see a pattern. That's what I'm primarily interested in. I don't want to see a pattern. Now, you might say, well, it kind of looks like a happy face, or here's a good rule of thumb. If you were to move one data point and that, or add a point or delete a point, and that would change your interpretation, you don't see a pattern. That's a good rule of thumb. And so here, if I was to add a point here, it would kind of like disrupt this U shape that I'm seeing. And so there's such little data here, I can't make a conclusion about the relationship between the fitted and residuals. Now, next thing we're going to look at is check to see if the residuals are normally distributed. All right, so what we want to see, ideally, the points would all be close to this line. This is the normal QQ plot. And when I see points away, that's a sign that I don't have normality. Now here, I think probably not normally distributed, probably has got some heavier tails than we would like to see, but this isn't horribly off. I don't have that much data. When we have less data, there's a little, we expect things to adhere less to a hypothesized distribution. Also, in these plots, by default, the largest 3 extreme cases are always labeled. So when I come back here, you notice I have Chrysler and Imperial, the Fiat 128, and Toyota Corolla. These 3 are plotted. And then I have the Chrysler Imperial, Toyota Corolla, and Fiat 128. Now this is the same 3 points came up, but this was a different calculation. So here we're looking at the largest absolute value in residual. Here we're looking at the largest deviation from normal on these 3. Those are 2 different calculations, but we see the same points are popping up. If the points deviate severely from a straight line, then that is a violation of the normality assumption, and I can't trust that F statistic. I can't trust the T statistics from the previous hypothesis tests that we were looking at previously. Now here we have scale location. So here we have fitted values, and here this is the square root of the absolute value of the standardized residuals. Similar calculation to the first one, but this is done in a slightly different manner. First of all, it's a standardized residual, absolute value, square root, and we're seeing the same 3 come up again. So I'm starting to think that these 3 might be outliers compared to the rest of the data set. Now, Cook's distance. This gives the Cook's distance for each observation. And if I have a lot of data, you can see that this would be a very crowded plot. Now, when I look at this, notice that the same 3 are popping up once again. This is very consistent with what we'll see with real data in real life. And so this is basically setting up a case that I might want to take another look at these 3, maybe omit them, maybe impute their values to make them less extreme. In real life, if I had something like this going on, I'd want to double check to make sure, were these measurements actually taken correctly? Is there something wrong with the data? And now here we have leverage, we have standardized residuals, and then we're going to have a Cook's distance contour plot placed on top of it. And basically by the Cook's distance contour plot is where we'll be getting things flagged the most. Now here we have leverage on the horizontal axis. This comes from the hat matrix. We have Cook's distance on the vertical axis. And so here, these lines tell us the ratio of Cook's distance versus leverage, uh, you know, the HII divided by 1 minus HII. And so, we can see, which ones are coming up. So the ones that have the largest ratio are the ones that we're going to be most interested in. Once again, it's the same three. All right, so now let's talk about simple linear regression. So my example that I gave you was actually simple linear regression, but I want to be a little bit more specific. First, I gave general multiple linear regression. Now we're going to go to a more simple case with just one predictor variable. The compute example I gave before, it's actually the same model. That's simple linear regression. I only have one predictor variable. And so in this situation, I have one predictor variable. Notice that I didn't bother with the subscript on it. Here I have the coefficients, I have the intercept, and then I have that error term accounting for all aspects of what's happening that's not accounted for by the data. We typically make the assumption that this is normally distributed with mean zero and constant variance. Now with multiple linear regression, we have more than one predictor variables. We have multiple predictors. All right, it's the same equation I showed at the beginning. And so here I'm going to, let's say that I'm interested in weight, QSEC, and automatic or manual transmission. Okay, so now let's go ahead and build this model. So now it's going to be a little bit tougher to interpret what's going on because when I have multiple variables, I have to assume when I'm making an interpretation that I've got constant on the others for this. All right, so we have miles per gallon depends on weight, QSEC, and automatic or manual transmission. And here we can see that weight has gone down in magnitude. So now it's, let's just say -4 instead of -5. All right, so this is saying when I take a more precise picture of the vehicle, of all the features of the vehicle, as weight increases, the miles per gallon goes down when I'm accounting for other variables. So it goes down by less. Now, QSEC has a coefficient of 1.2, and automatic or manual transmission has a coefficient of 3. Now, automatic or manual transmission, that automatic transmission is a 1, manual transmission is a 0. So this is saying that we're going to get 3 more miles per gallon on average when it's an automatic transmission. Kind of interesting. Here we see we have a stronger multiple R squared, but here's a little secret. That will always go up or stay constant if I include more predictor variables. And so I can't really trust this by itself to make an evaluation of my model. This evaluation, adjusted R squared, this takes into account the predictor variables I have. If I see a big gap between these two, and there's a little bit of gap, but not a lot, adjusted R squared will always be less than multiple R squared. If I see a big gap, that's a sign of overfitting. And once again, we get our F statistic. Now, here are the assumptions of linear regression. So first of all, linearity, this means that I've got the right equation. Whatever equation I have, I picked it. Now, do I have the right equation? We'll do model diagnostics to check to see, do I have the right equation? Does it look right? Does it smell right? Does it make sense to my stakeholders when I talk to them, my subject matter experts? But ultimately, we never really know. Independent. So we're going to make the assumption that the errors in the model, the residuals, are independent of each other. We're going to assume homoscedasticity, that is, the residuals have constant variance at every level of the independent variable. So we have constant variables with respect to, or constant variance of residuals with respect to our predictor variables. And then we're going to make the assumption of normality. And here we're going to assume that the residuals are normally distributed with mean zero and constant variance with respect to x. Now, These three are the ones we really need to have. Actually, it's linearity and independence are the ones that we need to fit a model. Otherwise, without these, this just doesn't even make sense. Homoscedasticity, like we need that to be able to get through some more analysis. And the normality is what we need for hypothesis testing. I can actually go without the normality assumption and still get a model, still interpret the coefficients, but I can't trust any of the hypothesis testing if the normality of residuals is violated. All right, so now to do with the assumption check, basically we run through diagnostics on our model. We're going to go through and just check to see, does this make sense? Does this look right to us? Now, something I like to do when I work on a real project is that if there is a predictive variable that's very important, preferably categorical, I'll go through and I'll color by that predictor variable. Or if it's not categorical, I'll go through and bin the continuous values. And I could do this for the target variable, or I could do this for a predictor variable. Either way, I find that this helps me find patterns I would have missed otherwise. All right, so now here is a residual plot. Now this is the raw residuals. And I kind of see a U shape, but realize if I was to move this point over here, then I would really not see a pattern. If you can move one point, delete a point, or add a point, and disrupt the pattern you think you see, you don't see a pattern. So use that trick quite a bit. Now, you'll notice that the automatic transmissions are the ones with the better miles per gallon. So they're on the right for the fitted values. That's consistent with that coefficient we saw earlier. Now, for our residuals, for hypothesis testing, we want our residuals to be normally distributed. So here, I'm just doing a histogram of the residuals. To me, that doesn't look normally distributed, but I don't have enough data to really say yes or no. It's light enough on data that I'll go ahead and accept it as being normally distributed for the purpose of proceeding through my project. And then we'll go through and do our plots. Once again, I'm coloring by the automatic transmission just in case I might find something. And, so here it's the same thing that we looked at before, but now I have a little bit more information with the automatic transmission included. And instead of automatic transmissions, I could bend, the target variable, I could bend a predictor variable. Now, when I have a categorical predictor, what's going to end up happening? Here I have two levels. I have manual transmission, which is a 0, and I have a automatic transmission, which is a 1 in the AM column. All right, so what's going to end up happening is that R is going to fit where the dummy variable, that zeros and ones, is equal to 0. And then what it's going to do, it's going to look at like a shift. It's going to shift the values by a certain amount for the cases where the automatic transmission column is equal to 1, where it's automatic transmission. So we can see that it decreases by 0.2 right there. Now, this hypothesis test is to evaluate whether this coefficient should be equal to 0. All right, that's a pretty large p-value, so I conclude that the automatic transmission coefficient is equal to 0. So I would go through for a real-life project, and I would remove automatic transmission from this weight model. And then I have all the other features I can use for it. So something that is important to always remember that when I have categorical predictor variables, I have a baseline level. And the coefficients for the predictor variable that's categorical are for the other levels shifting off of the baseline level. And now I can set up the order of my categories to set up my baseline. So what R is going to do is going to take the one that's by default, the very first one. And that is going to be the baseline level. And if I want to change that, if I want to control which one's baseline, I need to go in and make sure the very first one using a factor is set up that way. Now, what interaction does is that the slope of one variable changes in response to the value of another variable. So what I'm saying here is that the slope of weight will change depending on the value of horsepower. So here we're taking the point of view that horsepower is a constant value when we do this interpretation. Another way, if I reverse it, is that the slope of horsepower changes depending on the constant value of the weight. So if I treat weight as a constant, that is going to determine the slope of horsepower. So horsepower's slope changes depending on what the weight is. And so here I have like my baseline coefficient for weight in this model, baseline coefficient for horsepower. And now here, depending on the value of weight or the value of horsepower, whichever one I'm treating as a constant, I multiply this by that constant value and then add it to the slope of the other to get the interaction version of the slope. So slope, it changes depending on the interaction value. Now, something that we want to do, we always want to check for multicollinearity. So here, this is the idea that if I have one predictor variable, I don't need another predictor variable. That's our multicollinearity. Now, think about like degrees in Fahrenheit, degrees in Celsius. There's a perfect mathematical relationship with them. And so if I know it, if I'm building a model and I have degrees in Celsius, I don't need degrees in Fahrenheit because that's redundant. Now, things get more complicated when we have more predictor variables. The more predictor variables I have, the more opportunities for multicollinearity I have. So it might work out that this predictor variable is perfectly represented by these two when I have both of them going on, or these three, these four, something like that. Multicollinearity checks to see, hey, this variable right here, can I get rid of it? The bigger the variance inflation factor, the more I can get rid of it. So here, like displacement, so what this is doing is this is considering having all predictor variables in my model. And then I'm going to look and see which ones of these is like the best candidate to get rid of. Well, I look here, I see displacement is very large. All right, so what this is telling me is that the displacement information is redundant with other values in here. And so I would say, just thinking about it, probably, gears and horsepower and cylinders are probably going to be highly collinear with displacement. And so if I wanted to reduce this model that has all predictor variables, I would consider getting rid of displacement first. Then after that is cylinder. Now, if I want to further reduce my model, I have to go through and recalculate, because when this cylinder value was computed, it was using displacement in that calculation. If I remove the displacement predictor variable, then I'm going to get new variance inflation factors. And so then I'll have to go through and just redo it. After every time I kick out a predictor variable, I have to redo my variance inflation factor. Now we have the option of doing polynomial regression also. R makes this pretty easy, of where I just use the poly function. I specify the predictor variable, I specify the degree, and this function in R will give me orthogonal polynomials automatically, which is very nice. All right. So homework. For your homework, very simple. Take your data that you have, or some data that's interesting to you, and fit a simple linear regression model with several predictor variables. Build a model that's interesting and compelling to you, and then submit it. That's it. For my homework assignments, I do small, frequent assignments. This one is very small. Just build a model. If you want, interpret, dig into it, have some fun with it. That's all I've got for you. Life is short. Do math.